Hello, everyone. My name is Connor O'Brien, here from Boston University. I'd like to give a thank you to my colleagues at the University of Alabama at Huntsville and JPL. They helped me, drink from the fire hose of machine learning in a relatively short amount of time. I'm going to be talking about non-deterministic models of solar wind propagation from the first Earth-Sun Lagrange point to the Earth, to give an overview of the system, since we've been looking at images of the sun very close up relatively so far. This is the geometry of our situation. You have the first Earth-Sun Lagrange point, about 230 Earth radii, or 1.5 million kilometers from the Earth. The relative positions of the bow shock and the magnetopause around the Earth are shown there. The only continuous in situ solar wind monitors are located at the first Earth-Sun Lagrange point. There are none around the Earth because of orbital dynamics limitations. So if you want to assemble a complete record of solar wind conditions at Earth, you're going to have to propagate those conditions that were measured at the first Earth-Sun Lagrange point, those 1.5 million kilometers to the Earth. This is, of course, after they've already traveled 23,000 Earth radii, so this is very much a last mile sort of propagation problem. But even so, it is not a simple task. So as we know, the solar wind is highly structured, has all sorts of wonderful physics going on in it. In particular, it's considered to be a sort of spaghetti almost of flux tubes, the boundaries of which are shown in these two diagrams here from Joe Borowski. On the left is a sort of sun's eye view of the Earth's magnetosphere system, and on the right is a side view of the system. And as you can see, these flux tubes are around 50 to 70 Earth radii on diameter on average, and that's about the same size of the magnetosphere system, right? So what this can cause is, if you're looking at solar wind monitor data, for instance, on the top here is magnetic field data from ACE, and on the bottom is magnetic field from WIND. These are two spacecraft at the L1 point. You can see that they can be measuring very different plasma and magnetic field regimes. So on the top, you can see that ACE is measuring steady negative BZ for this period, and WIND is measuring steady positive BZ. And if you're trying to say something about storms at the Earth, you better get this right. You better choose the right spacecraft here. And the current propagation algorithms, which you may have heard of, called Omni, or rather these algorithms are used to assemble the Omni database, are these solar wind conditions measured by the solar wind monitors at the L1 point that are then propagated to the bow shock with a simple physics-based analytical algorithm. In addition, there's instrument cross-calibration, all sorts of things go into this data set, and it's broadly considered to be very useful by the community. So in all of the publications in space weather and space physics, JGR, around 42% of them cited Omni data in their paper. However, this algorithm has notable limitations. It's almost 20 years old at this point, and those limitations include the fact that the physics that they use in their propagation algorithm break down when, say, a fast solar wind stream overtakes a slow solar wind stream. The algorithm breaks down at that point. We know there's all sorts of physics that goes on in that interaction, but they sort of come to the bow shock as is. In addition, the Omni dataset has a notable limitation where it does not include physically meaningful uncertainties on its values, which we know are of the utmost importance for space weather forecasting and prediction. This sort of motivates the central questions of this work to basically train a neural network to reproduce observations of the solar wind near the Earth, in our case from MMS-1, given inputs from a spacecraft at the L1 point. So, of course, this requires a data set at the Earth, a data set at the L1 point, and a sufficiently representative network algorithm. So to go through that in order to assemble a data set of solar wind conditions near the Earth, we partitioned all MMS-1 data from 2015 to, in this case, 2021, although we're working on that last year, with a classification algorithm that looks at the 3D ion velocity distribution function. So these are our representative cases of the 4 categories that this algorithm can discern. This algorithm was trained by Vyacheslav Olszewski. And you can see the solar wind distribution function, where it's a very tight distribution function oriented along the magnetic field. You can see the ion force shock, where you can see the solar wind in the center, and then counter-streaming ions around the outside. The magnetosheath, which is a very broad distribution, thermalized. And then the magnetosphere, which is sort of isotropic. Using this algorithm, we partitioned MMS1 data into 78,109 samples on the day-side magnetosphere. A 3D distribution of those is shown on the left, and then cuts in these axes are on the right. And the features that we selected from this data set are the 3-component magnetic field, 3-component velocity, and electron density. We used electron density rather than ion density because MMS's fast plasma investigation actually has errors in the solar wind for ion density, becomes unreliable, as well as ion temperature. So both of those were excluded from our data set. For our input data, 100 minutes of wind data is assembled for each target. This 100-minute time series begins 125 minutes before the target and ends 25 minutes before the target. A stride of 25 minutes for time series jargon. And then for this data, we include, again, the 3-component velocity, in this case, ion density, ion temperature, magnetic field, and the relative positions of the 2 spacecraft. This is so that we can give the network information about the propagation distance and information about the speed and sort of what parameters we want to be propagating to MMS. The architecture that we utilized here is based on gated recurrent units, or GRU. These are a very well-tested sort of, some would say, old architecture, where we step through these 60 units of the wind time series with this GRU network, and then we feed it the features that the GRU identifies to a 3-layered, fully connected network shown in gold. And then the fully connected network outputs not individual sort of analog deterministic predictions for each parameter, but rather a mean and a standard deviation that then defines a probability distribution for each of the parameters in the MMS data. So that's the ion velocity, density, and magnetic field. Yeah, and also to mitigate overfitting, we implemented, standard procedures such as dropout and layer regularization at each step of this process. But yes, the sort of novel technique that this architecture uses is, again, that the last layer defines a probability distribution and not simply a deterministic single point prediction. In order to sort of train this network, one of the limitations of non-deterministic algorithms is the fact that it can be difficult to select a loss criterion. As you can see, sort of scoring metrics usually take the form score equals prediction minus observation, to use words, right? For deterministic predictions and observations, this formula becomes the absolute error. Learned it in grade school, right? For prediction, so that's what you can see on the left here, y observation minus y prediction. For a non-deterministic output here, this formulation becomes less obvious, shall we say. For our purposes, we used a function called the perfect. By formulating in terms of the cumulative distribution function of each of these parameters, we allow the generalization of the absolute error, the continuous rank probability score, which is simply the sort of integrated distance under the curves of the continuous distribution functions here. So that's the CRPS is shown in blue for a deterministic prediction as well as a probabilistic Gaussian prediction on the right. The formula is given up here at the top, and it reduces to this sort of long but analytical expression for a Gaussian probability distribution. This function is better than, say, the negative log likelihood for training models because it systematically punishes over and underconfident, or symmetrically punishes over and underconfident predictions. Unlike the negative log likelihood, it also collapses to the mean absolute error for sigma going to 0. So you can use it for deterministic as well as probabilistic predictions. And it has the same unit as the variable of interest, which helps humans read the output. Through training that architecture using that CRPS as the loss function, we get outputs for the 7 features in the MMS data that we would like to predict. Joint distributions of the MMS data on the x-axis and the neural network predicted and Omni predicted values on the y-axis are shown here. A perfect prediction is represented as a straight line. And in the top left, although it's probably really small, are shown the CRPS values for each model parameter pair. In the interest of time, I'm just going to zoom in on dynamic pressure. So you can calculate dynamic pressure for the MMS data, the neural network predictions, and the Omni predictions. And we're sort of zooming in on these joint distributions here. And what you can see is that we are, this very simple network architecture is outperforming Omni by a factor of 2 in the CRPS score. And you can see that Omni is actually systematically over-predicting dynamic pressure, especially for high dynamic pressure values. Additionally, you can evaluate time series, and this is where sort of this is sort of interesting to see the outputs of these models. So here you can see MMS data in a solid line for this co-rotating interaction region shock that was observed, where a fast solar wind stream interacted with a slow solar wind stream. So ground truth is in solid. Our neural network outputs are in the dashed and shaded regions there. And then the Omni predictions are in the dotted line. What you can see is for quiescent solar wind here, our values are, fairly stable, match fairly well, and are within the uncertainty bounds. But when you have a interaction region here, the uncertainties predicted by the model go way up, and especially for the x component of the velocity. This is due to the fact that the output of our models are a symmetric Gaussian about the mean. What you can see is the mean actually tracks fairly well with the velocity here. But in order to capture the dip, it has to symmetrically expand. So this informs future work where instead of a Gaussian probability distribution, to output of a probability distribution of a variable or a more flexible shape would be desirable. Yes, and I think I've gone a little bit fast, but in short, a record of the solar wind conditions at Earth requires a propagation algorithm, state-of-the-art versions of which have limitations in the form of breaking down in certain situations and not providing uncertainties, or at least physically meaningful uncertainties. Modern algorithms can actually assemble more accurate predictions of the solar wind and move past these limitations, and can also provide physical meaningful uncertainties and sort of address all of the limitations with current models, or current algorithms. And with that, I will take questions.
Thank you so much. Thank you. Questions, comments? That was a very interesting talk. One over there.
Thank you. Good talk. I wanted to ask about how do you know that Omni has physical out-of-sequence arrivals of solar winds?
So it has physics. So we know that it has out-of-sequence solar wind arrivals because that's actually directly from the Omni team. They actually call that out on their website for the algorithm. Basically, I didn't go into it for time, but the way that Omni works is it takes the time series of the magnetic field measured by the spacecraft at L1, and it uses minimum variance analysis to, oh yes, closer, thank you. Uses minimum variance analysis to determine sort of the plane that that magnetic field is in, right? The plane in which the magnetic field is varying the least for some, you know, chosen time length, right? And then that plane, you know, they assume that the plasma parameters and all of the parameters of interest are constant in that plane. And then you have a velocity, right, in that plane. You just propagate that plane forward ballistically with that velocity. What that means is if you have, say, a plane with a slow solar wind speed and then a plane with a fast solar wind speed, that fast plane can actually arrive at the Earth before the slow one in their algorithm. Or if it's very highly inclined, right, you might, and very far off the Sun-Earth line, you might actually hit first. And we know that that isn't how supersonic flows work, right? You can't just pass through yourself without modifying the plasma parameters in some way. Okay. But currently, if you want to exclude regions like that from the Omni database, they have a negative delay time. And that's sort of the flag that they say that you should use to exclude times of where they predict that the solar wind is passing through itself.
Okay. One first question: the last plots, the shadow colors that you shown around the dashed lines, are the uncertainties? Yeah, is that the uncertainty? Like
yes, okay. That's the 1 sigma uncertainty.
Okay, thank you.
So there was one question across the aisle over there.
Thanks, great talk. Just to follow on from that, so in the ML model, does that solve the problem of out-of-order arrivals?
My answer is yes, for some of them. Essentially what it's solving is the physics of these interacting regions, right? Whether it's that the spacecraft, whether it's two flow parcels that are next to each other, discerning which one ought to be the flow parcel that arrives, or if the flow parcels are interacting, choosing or learning the physics of that interaction, right? I didn't show this up here, but one of the times when our algorithm does break down is, say, if the spacecraft is entirely not within a flow parcel that would hit the Earth. So what we're trying to do is add in all of the solar wind monitors, well, L1 to our input data set, and hope that one of them is in a flow parcel that actually hits the Earth. Good question.
Great, and just one other technical question. What strategy did you use to split your train and test data? Because we've heard earlier on how that makes a huge difference, and I was wondering what was done there.
Yes, so the way that we split our train and test data set is we broke our full data set into chunks of twice the length of our input data, so that all of our inputs are non-overlapping. This is actually a big problem with time series predictions, is you can actually get leakage between your train and test data set if your inputs are overlapping at all. So we were very careful to avoid that. And then we tried splitting the chunks in terms of time. Say take the last year of the data as our test, and then the second to last year is our validation. We found that it didn't make any difference whether we randomly split them or split them according to time, since we don't actually cover a full, I think it's because we don't actually cover a full solar cycle. It's 2015 to 2021, so sort of. But I guess there isn't enough of a difference between the start and the end where actually splitting that way makes a difference. So, yeah.
Okay. Any quick comment? Yes, certainly.
Yeah, just a clarification. So, what happens if you have a structure that's passing through? I mean, obviously you can split in the middle of that. Do you like go in by eye to make sure that you don't split your data in the middle of a structure that's passing by, or that doesn't matter?
For the train and test data set, we don't look to make sure that we're not splitting up structures in that. what I mean by splitting up the train and test data sets so that they're non-overlapping is so that the input time series is non-overlapping from the start and the end of a given batch of data. So if we cut a structure in the middle of that, it shouldn't affect our data or affect the model outputs, since it's just which set we assign the batch to, right? And it's assigned such that if there is a structure, it should be entirely contained within one of the chunks. So.
Okay, well, let us thank Connor again. And